open up Recap, you're going to get that screen that we saw. And from that, you basically start a new project. You click on the new project there, and then you import what it is, for instance, activity. And then you have to basically import from a particular location. You have to see where that location is on your PC, and then import that text file from it. Okay. Once you imported it, this is where you're going to get some information here. This is the clip point. This is for intensity clipping. Intensity is where that those colors that I represented showed how it is, right? That intensity and that clipping there would only work for laser scanners. In your cameras, you don't have that information about the intensity. So this doesn't apply to this for your application, because the point cloud that I've uploaded here is a point cloud from what is it called, a structure from motion. So it has colored information, not intensity information. However, regardless, I don't ever use this information and this clipping, because intensity is very, very sensitive and it's very distorted. So it's very hard to make a judgment that this point and its intensity is not good or is inaccurate. So it ends up removing a lot of the points, which we're going to talk about it in the next sessions as well. So what I want you to do is to go to the text option. Here, the points that I've uploaded is directly from CoMap. It has 3 lines. You can here select that you don't want, and you want to skip, let's say, a number of lines. So here it already identified that automatically that 3 lines need to be skipped, but you can change that if it's more or less, or if it didn't detect it properly. The second part is that, of course, you can also change the unit here if you have that let's say, information prior to it from elsewhere. The other one is that, of course, you can get the delimiter as well, but you need to now change the first one. It's thought that's the first one, which is supposed to be the point number. It's identified that as your X. That's not it. So you can identify either as none, or you can do a classification. So you have to change that. I've changed it to none here. You change the first one to X, the second one to Y, the third one to Z, and then the fourth one is going to be R, which is color. The second one would be G, and then the last one, the next one would be B. So you have the RGB, you press on import files. It starts importing it. If you have multiple scans, in the next one, it starts indexing these scans, and then afterwards, I think it starts first registering, and then it starts indexing these scans, but we don't have that problem. So you're going to get something like this. You can take a look at it. And you can play around with the recap scene on basically how you're able to accommodate. Now you can play around with it. You can toggle between the perspective and orthographic. For instance, for orthographic, it's better because now the overall proportions are correct rather than a particular perspective. You can now change the background as well. For instance, I typically like to do it white. Sometimes it might not be as good, but oftentimes it's good, but you can still keep the background however it is as well. Were we able to upload this? Yes? Good. Any questions so far? It was pretty simple, right? Excellent. So the next part is that I want to show you how we can use this fence here command on the bottom to be able to extract or let's say segment particular regions. So you can use this, and you can use it either by means of a window, which is a rectangle, or you can use a fence, which is basically a very particular fence that you can basically use and draw around it. So now I want to isolate and segment this particular column manually. I do that, I press enter, and then it looks like this. Then you can go to region and add new region. So you can put, let's say, column, and press OK. Then if you take a look at the area on the right there, it looks like some pages. So you can go to the scan position, and you can actually remove the unassigned points in terms of its visibility. You can also remove it completely, and you can also play around with the color that you want it to be represented. It wouldn't change the color. So if you click out of it, it would change. It would, you know, have a let's say similar color to how it originally used to be. But for the sake of understanding and taking a look at it, this is how it is. So now that's how you can basically isolate a particular item there. This was quite simple because it didn't have anything else around it. You basically can take a look at it from the top and then, you know, go through it like that. Were we all able to go through and segment? Yeah. Excellent. Good. The next part is planar surface detection. So you go to the plane, then you have to indicate what depth it is. This is where it becomes important. See, I here put like 1 millimeter. How do I know it's 1 millimeter? It's not 5 millimeters. It's not 10 centimeters. I don't know. I don't know what the noise level could be, especially with structure from motion. It's quite challenging to be able to identify that, particularly if you just have a point cloud. If you have it from outside, you would be able to get an idea of how much this accuracy or inaccuracy is. But if you don't have any information and you're just given a point cloud, you need to do some sort of surface analysis to be able to get an indication from that. So this is something to be mindful of. So what you need to do is, once you've selected that plane option and you've identified the depth, you click on 3 points, and every 3 points you would be able to get a plane. And you see a lot of these points were not identified, and this is where you have to play around with it. 5, let's say, millimeters. This looks a bit better, but there's still some points that you can see that have been, let's say, identified. You can play around with it even further. And this is where I like to, you know, play around with it myself. I like to actually use my own software and my own methods, because for that, I don't want to rely on, let's say, changing this from 5 millimeters to 10 millimeters to see how it's going to look. I want the computer to mathematically make that decision and that determination for us, instead of us going inside of it ourselves and just changing it around. So I'm just increasing, for instance, the size, and you can see that, for instance, while I put it for 20 millimeters, a lot of these points that are not on this plane have been identified as this plane. If you now revert it back to the 5 millimeters, it looks much better and much cleaner, and it's detected the plane from the remainder. And this is, of course, very dependent upon how the rest is. And you can identify that as a new region, say plane 1. Press OK, and this is going to be your plane. Then you can remove it just as a visibility. Then you can perform the same task for, let's say, the other ones as well. And what I wanted to show you here was basically, this is plane 2. The plane 3, you go 3 points. And then with the same ones, because you took different points and different planes, you had a different response, right? I had to, again, redo it. And then if you play around with it, you see like a lot of these were not still extracted, even though I tried to make that connection twice and the selection twice. So now I had to change it to 10 millimeters here, just so that it would be a bit more presentable here. So this is what we have to be paying attention to, and this is why we're doing some analysis outside of here, so that you can see that, you know, manually, if you want to do this, what is the value of actually spending that much time into that manual process? And the other thing is it even going to be accurate? If I do it, is it going to be the exact same as if someone else is doing it? So that is where we have to be able to utilize some sort of system. And more importantly, it's not that important to do this, so a lot of people don't do it. So now you have something like this after you have segmented, let's say, the planes. And Recap, I don't think it has anything else, let's say, for other more complicated, let's say, cylinders. It only has it for the plane. But the cylinders and whatnot can also be represented in similar fashion. So everyone was able to kind of segment the planes, identify those. Yeah. Good. So here, I wanted to talk about the segmentation process in CloudCompare. If you now remove the recap and then add the CloudCompare to it, the segmentation process is quite simple and straightforward. So you skip the lines that you don't want, you can play around with it. And then here you can select either scalar or RGB, which, because this is RGB, you want to do the RGB. Then you go in, zoom in, find where you want to extract the information from. You select your point cloud from the left menu there where it says DB tree is selected, and you get this scissor. So from that, you can play around and pick. You have to typically pick this one. So this one is where I think, yeah, this is where you can get the inside of it. Or sorry, I apologize. This is where you can select whether you want a polygon or, like, let's say a rectangle. And then once you've identified that region, you right click, it isolates that region like this. And then you can either press segment in or segment out. Okay, segment in is that inside of this region or outside. Of course, we want out inside. And then once you are satisfied with it, then you press this check button there that you're satisfied. And then if you want to make the rest of the clouds invisible, you basically go and uncheck that from the left screen there. And what I want to talk to you about before we go to next session, essentially, and the reason why I actually talked about the segmentation here and gave an idea is because we're going to talk quite a bit about the analysis of these and how important there are, and why can't we just, you know, do it manually and whatnot. I want to kind of give you a bit of an idea of why it's not possible to perform it manually, or it's quite tedious and challenging. Or why do we need to create new methodologies for these types of aspects, and why I have actually spent, let's say, the better part of my PhD back when I was basically doing my PhD on how to analyze these point clouds in order to extract information. And initially, my whole focus was on planar surfaces. So if you, let's say, take a look at the plane detection in CloudCompare, this is an example. It's actually a very established method. It's called RANSAC, and this is for shape detection that they use there. Because this is an open source, it's not like they are getting paid, or they're creating these methods, they use available, very established scientific manuscripts in order to perform these tasks. So they're using a particular method that I've actually compared mine to, and I'll let you see it for yourself. So you have to go to the plugin section, and then here you have RANSAC shape detection. RANSAC stands for Random Sample and Consensus. Meaning that it's for, if you want to detect a plane, you know that the plane needs to be, if points are following the same plane, they need to follow the majority of that particular plane in order to be detected as one single entity. What RANSAC does is that it says, okay, you want to detect a plane. How many points do you require to detect the plane? We need 3 points to detect the plane. It randomly selects various different combinations of 3 points, fits a plane to each and every one of these. And then what it does is it now extracts the plane that has the majority of the points that had complied with the original 3 points that it had detected from. So this is what we call random sample and consensus. For this, you need some estimation of your standard deviation or the noise, as we saw in the other one. It doesn't, the original methods of RANSAC does not do that automatically, and actually it's going to be quite tedious to do that automatically and perform that automatically. So what ends up happening is that you go and you click on RANSAC shape detection. And I don't even want to make this complex and say, go and search for spheres and cylinders. I'm saying we only have planes. Go and detect planes. And this is where you have all of these nice information. How many points do you want? The minimum, for instance, per the primitive. What is the normal deviation from the original one? All of these types of things. And that's where that standard deviation that I mentioned, all of these come from. So if you put 5 degrees, it would look like this. So I think it detected 18 planes for something that really should have 4 major planes. You might see some plane-like structures, but they would all have less than 500 points to it. And we clearly mentioned there that anything less than that, we don't want that. And some of them are weirdly shaped, some of them are intertwined from the same plane, but it doesn't have a good merging strategy to it. So if you check, I think it was 18 or something planes that it detected. Four, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah. Now let's, change this and let's play around with it and change it to, say, 25 degrees. Now it's gotten a bit better. So now this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So from the 18 original, now it's removed to 13. Meaning 5 of those planes that were arbitrarily added there were just removed. Now, if you change this to, let's say, 50, yeah? Now this is a bit better. You still have more points, more planes that you require. And you have, I think, 7 here. 7 points, planes, instead of the original 4 planes that it needed to actually identify. Now, the problem with this is that we had to play around with 3 different values of that, and it still didn't give us the good results that we really wanted. So that is the sad part about this, that even academic papers that get peer-reviewed and published, when you implement this, even on a simple problem like this, it still doesn't do its justice and it still doesn't do it properly. So these are the types of things that I'm going to talk about to you next session and the sessions after. This is a paper that I've published in recently about field information modeling, which is a topic of our lectures. And essentially, one of the methods that I proposed there was a simple method to be able to detect large planes from point clouds. So for something like this, what we do is we typically have to first identify what neighborhood around each point we want to use. So these neighborhoods would be utilized in order for us to extract curvature information. So for this, we extract planar surface information. For that, we need the normal vector of that. So that is the easiest way to be able to detect large planar surfaces. Once we get from every point, what we do is, this is the neighborhood definition. Basically, the color represents what neighborhood around every point or around that particular point has been selected. This is basically, if it's blue, that means that only 2.5 centimeters around it has been detected or has been extracted. And then using that, we get that neighborhood out and we remove everything else. For every neighboring point, what we do is we find the normal vector. So the normal vector of that is eigenvalue decomposition of the covariance matrix of that. And you find the smallest eigenvalue for that. The eigenvector that corresponds to that smallest eigenvalue would give you the normal vector. So the normal vector, once you get it, how these types of objects are detected and how I have proposed to detect these types of objects. These are planar surfaces, let's say. These are floors. These are walls around it. The simplest and the most accurate way is this: to be able to find where the majority of the normal vectors are directing to. So you have this plane and this plane here. For planes that are separated, the normal vector is still in the same direction. Okay, what that means is, if you have 2 planes here and 2 planes here, our expectancy is that the normal vectors are directed in either this or in this, right? So this is why and how we are able to do that. What we do is we take the distribution of our normal vectors out. We go and we find where the mode of these normal vectors are. We first go with the larger one, and we find where the normal vector is. What I do is I rotate it so that the z-axis is parallel to the direction of that norm. What it looks like is something like this, meaning that now if I do that normal vector towards the direction of the top, our sides here are going to be represented by these 2, if we just look at it in terms of its height. Once we do that, and this is basically where the normal vector is going to direct. And then here is going to be a majority, and here is going to be a majority. Why? Because all these surfaces around here have no points associated with that. Okay. Once we have that, then we also again have to detect the mode here. And then once we detect the mode, we get the points around that mode. And then we perform a robust plane fitting that I've proposed in that basically manuscript there. And from that, we get that and we detect these. So this is an automated process. It's very simple, easy to follow processes, basically stitching together some good information. Let's take a look at, as my final thoughts today in this session, on how it compares to Recap, the planes that we originally detected using Recap manually, which I had to select 3 points. And doing that, my method takes approximately even less time than that, and it hasn't even been optimized for for speed. So these are the original planes. I'm going to basically take a look at two planes, and these are what I have detected using my method. If we take a look at this plane, for instance, if we go and zoom in, we're going to see that my method, which is the yellow one, did not detect all of these other basically outside of these realms that the manual method that we had proposed there had actually done. And I think I changed this to white so that we can have a better view of that. And you see even on the bottom there, all of those other ones are from the manual method that we've detected. So all of these points that do not belong to that plane in the manual basically method that we went through today in this lecture, we see that it's significantly different. And that was an automated method, very simple method to implement. And you can utilize that and extract the information that you want from it as accurately as possible. So this is why we're basically doing this. This is why I'm going to try to teach you some of these methodologies that are new, no one else knows about it, or if they know about it in the sense that it's very, very up and coming. But it's good because you're going to get some exposure to it. And then hopefully you would be able to utilize it on your day-to-day work on the construction site, or you would be able to recheck the work that is existing there as well. So this was the